Get to it. Okay, everybody, we are moving right along. I think we are now in day 3 of our discussion of the overlapping generations model. Today I want to break the class really into 2 parts. So if you guys remember, in the last class, we spent the last bit of class talking about the canonical version of the OLG model, right? This is the one that has logarithmic preferences and Cobb-Douglas production. We looked at that version of the model because it was easy to solve analytically, right? In fact, we can show that it boils down to something that looks a lot like the solo growth model in the sense that there's a unique steady state and it has this kind of global convergent dynamics to the steady state. So today what I want to do is take a step back and just look at the slightly more general model that has CRRA preferences and Cobb-Douglas production. And for the first half of class, do a proof of the existence and uniqueness of the steady state. The global asymptotic stability of that steady state, I will leave for you all to look at. It's the proof should be sketched out in pretty good detail in the notes. If I have any time left after doing the proof of proposition 1, we will move on to a discussion about this kind of bizarre feature in the OLG model where the competitive outcomes are not necessarily Pareto optimal. They're not necessarily, in fact, they're usually going to be situations where the allocations are not going to be the same as what a benevolent kind of social planner would select, which is a prediction that this model makes that's very different than the neoclassical optimal growth model we're going to start talking about in the next few weeks, okay? And that all stems from this weird externality in the model that I kind of touched on in the last class where generations that are not born yet in the current period are going to be influenced by the decisions that we make because the prices that they face, in particular the return to capital, will depend on decisions we make about how much to save today. Those externality effects can cause individuals to over-accumulate capital, that is to save too much in this model. I'm going to try to do today a short sketch of a proof that illustrates that the competitive equilibrium in this model is not going to be Pareto optimal, that we could actually rearrange allocations in a way that makes all generations strictly better off. That is going to lead into a discussion in the next class about how fiscal policy can be used to address these types of distortions or externalities in the model. All right, I might not be able to get through all of that today, but that's kind of where we're headed. Is everybody kind of clear with what we're doing? Okay. All right, well, let's look at proposition 1 then. It says that if you consider the OLG model without technological progress, let the utility function be constant relative risk aversion form and the production function be Cobb-Douglas, then there exists a unique steady state equilibrium where K star, the steady state level of capital, is finite and it satisfies the following equation that we derived in the last class. So I'm just going to recopy it here, but not go again through the derivation. So 1 minus alpha A times K star to the alpha minus 1 is equal to 1 plus n times quantity, 1 plus beta to the negative 1 over theta times 1 minus delta plus alpha A K star to the alpha minus 1. That whole thing raised to the theta minus 1 over theta, end bracket. That right-hand nasty term there is that psi t plus 1 term that we derived in the last class, I believe. Okay, let's sketch a proof of this. And I got to warn you, the algebra is going to be a little bit tedious here. So just try to stay with me as best you can. And if something doesn't make sense, I would encourage you to go back over it again later. Okay, how do we solve, or how do we prove the proposition one in the solo model? First, we looked at existence, and then we tackled uniqueness, right? So let's start with the existence component of this proof. How can we prove that a steady state value of capital that satisfies this equation even exists? Well, what was the strategy that we used in the context of the solo model? You guys remember?
Yeah, we showed the another condition involved intermediate.
That's right. So in short, there was a mapping that we can devise from the key steady state condition. And then Tavoy, like you said, we analyze the behavior of that mapping at these extreme points. That mapping has to be continuous given the continuity in the production function and utility functions. And therefore, we can appeal to the intermediate value theorem to prove the existence of a steady state, right? We're going to do something very similar here, but it's going to be a little bit more complicated because that mapping depends on the values of certain parameters, okay? Let me define this function g of k as the following. It's 1 minus alpha a k to the alpha minus 1 divided by this nasty thing in squiggly brackets here. So if a steady state exists, then what must it satisfy? G of k star has to be equal to 1 plus n. Notice in defining G, I've moved all of the k terms basically to the left-hand side. That's going to be helpful because now the right-hand side is independent of k. That's the intermediate point we're looking for here in this mapping. Okay, now as Tavoy suggested, what we want to do is analyze how this mapping G behaves at extreme points. So let's look first for large values of k. What is the limit as k goes to infinity of G equal to? Well, what does the numerator look like? K to the alpha minus 1. Alpha is less than 1, right? So that is a negative power. So a huge value of k in the numerator is going to basically send the numerator to 0, right? If alpha minus 1 is a negative power. Divided by, let's see, 1 plus beta to the negative 1 over theta times 1 minus delta plus alpha a k to the alpha minus 1. Well, there is that negative power again. And so that's going to send that last term in squared brackets to 0 raised to the theta minus 1 over theta. Well, that is 0 divided by some positive number, right? 1 plus beta to the negative 1 over theta times 1 minus delta to the theta minus 1 over theta. So that's equal to 0. Let me draw what we're looking at over here on the right-hand side so that we can see where we're going. So here's k, here's g of k. What have we discovered? That for large k, g is really close to 0. What about the limit of this expression as k goes to 0? Well, in the numerator, we have this negative power, right? So what is a very tiny number raised to a negative power? That's going to be a huge number, right? That's 1 over a huge number. I'm sorry, 1 divided by a really tiny number, right? So the numerator of this expression goes to infinity. What happens to the denominator? Well, it's 1 plus beta to the negative 1 over theta times 1 minus delta plus infinity in this case raised to the theta minus 1 over theta. You guys understand that? So k huge, k to the alpha minus 1 goes to 0. K very small, k to the alpha minus 1 goes to infinity. Well, what do we have here? We've got an infinity over something. That something is going to depend on this exponent, theta minus 1 over theta, the sign of which is going to depend on whether or not theta is bigger than, equal to, or less than 1, right? So remember in the last class when we looked at these different income and substitution effects and how they depend on the risk preferences of agents? Well, we're going to have to think about cases here. If theta is bigger than 1, this is a positive exponent. If it's less than 1, it's a negative exponent, in which case you get very different behavior, right? Well, what happens for the case in which theta is less than 1? Let's do that case first. If theta is less than 1, then this whole expression becomes infinity over, let's see, 1 plus beta to the negative 1 over theta times 1 minus delta let's see. If theta is less than 1, well, let's just do it like this. Hold on. 1 minus delta plus infinity, that's an enormous number, right? Raised to the theta minus 1 over theta. If theta is less than 1, then this is a negative exponent. Well, that's the same thing as saying 1 over 1 minus delta plus infinity raised to the positive version of that exponent. That is 1 minus theta over theta. I've just flipped it, right? Okay, so that becomes an infinity over, let's see, 1 over 1 minus delta plus a huge number raised to a positive. Well, that's just 0, right? So this becomes infinity over 1. That's a huge number. So for the case in which theta is less than 1, g of k goes to a very large number. What about if theta is exactly equal to 1? Well, then you get a big number in the numerator over a 1 plus beta to the negative 1 over theta times 1 minus delta plus infinity, but that's going to be raised to the 0 power, right? If theta is equal to 1, then theta minus 1 over theta is just 0. Well, anything to the 0 power is just equal to 1. So this becomes infinity over 1 plus beta inverse, actually. Right? If we set theta equal to 1, well, that is also a huge number. So if theta is less than or equal to 1, g of k is very, very large. All right, what if theta is bigger than 1? Well, numerator is still infinity. What's the denominator? 1 plus beta to the negative 1 over theta. But this time it's going to be 1 minus delta plus infinity raised to the theta minus 1 over theta. That's now a positive exponent since theta is bigger than 1. So you get what? You get infinity over infinity. And now what do? How do we evaluate this limit if we have a large number on the top and a large number on the bottom? You got to use L'Hopital's rule, right? Okay, so that means the limit as k goes to 0 of g of k is equal to the limit as k goes to 0 of the derivative of the top with respect to k over the derivative of the bottom with respect to k. Oh boy. What's the derivative of the numerator with respect to k? It's alpha minus 1 times 1 minus alpha, a, k to the alpha minus 2. What is the derivative of the denominator with respect to k? That is theta minus 1 over theta, beta to the negative 1 over theta, quantity 1 minus delta plus alpha a k to the alpha minus 1 raised to the, let's see, theta minus 1 over theta minus 1 becomes negative 1 over theta. Chain rule times alpha minus 1 times alpha times a times k to the alpha minus 2. You get really good at taking derivatives in macro if you do it enough. Some of this stuff is going to cancel, fortunately, right? Here is a k to the alpha minus 2. Here's an a k to the alpha minus 2. I see an alpha minus 1 and an alpha minus 1. So this becomes the limit as k goes to 0 of, let me bring this alpha to the top. It's 1 minus alpha over alpha divided by theta minus 1 over theta, beta to the negative 1 over theta, times 1 minus delta plus alpha a k to the alpha minus 1 raised to the negative 1 over theta. We should be able to sign that, right? The top is just 1 minus alpha over alpha. What is the bottom? If k goes to 0 and it's raised to a negative power, then the expression in brackets goes to what? Infinity. And then if that is raised to a negative power, the whole thing goes to 0. So this becomes constant over 0 is a big number. So regardless if theta is less than, greater than, or equal to 1, g of k is going to be a huge number. Let me make sure I got that right. K goes to 0, then this becomes 1 minus delta plus infinity to the negative 1 over theta. Well, that's the same as 1 over 1 minus delta plus infinity raised to the positive 1 over theta. That's going to be basically 0 to a positive exponent, which is 0. Yeah. Now, g is, let me go back up here to my graph. We know that g is continuous because the underlying functions are continuous. So that means by the intermediate value theorem, we know that there exists some k star between 0 and infinity such that g of k star is exactly equal to 1 plus n. 1 plus n being a constant between 0 and infinity, right? So imagine drawing 1 plus n on this graph. We know that this function g has to intersect the 1 plus n line at least one point. That's where the steady state is going to be located. Now, of course, in drawing that picture, I made an assumption, right? That g is strictly decreasing, so that there's only one intersection point between g and 1 plus n. In other words, I've assumed that the steady state is unique. We can't make that assumption. We need to prove it, right? So let's do that on the second part of this proof. That is uniqueness. How do we prove uniqueness? There's no easy way to do it. You just have to plug through the derivatives, right? We need this mapping g to be strictly decreasing. In other words, we need to show that the derivative of g with respect to k is everywhere negative. Oh, Lord. All right, we've got k's in the numerator as well as the denominator. So I don't know how to do the quotient rule. I'm going to do the product rule. So the derivative of the top, again, is, let's see, alpha minus 1 times 1 minus alpha times a k to the alpha minus 2, divided by the denominator, which is 1 plus beta to the negative 1 over theta. Now I'm gonna cheat here, okay? I'm gonna just say times this thing in squiggly brackets to the 1 minus 1 over theta, because I'm lazy. I don't want to write that thing in squiggly brackets 100 times. Okay. Let's see. We've got to do the product rule, so that's going to be minus then the numerator, 1 minus alpha a k to the alpha minus 1, divided by the square of the denominator. So that's 1 plus beta to the negative 1 over theta times the thing in squiggly brackets squared. But now we have to do a chain rule argument. We have to take the derivative of the denominator with respect to k. Well, we did that on the last page, actually. It was theta minus 1 over theta times beta to the negative 1 over theta times this thing in squiggly brackets I made a mistake, didn't I? The thing in squiggly brackets is raised to the 1 minus 1 over theta. And that whole expression is squared on the bottom. So it's theta minus 1 over theta, beta to the negative 1 over theta, times the thing in squiggly brackets raised to the negative 1 over theta. We subtract the exponent by 1, and then you multiply through the chain rule argument. So it's alpha minus 1, alpha a k to the alpha minus 2. Okay, that's really, really hideously ugly. I have no idea how to sign, well, I do know how to sign that, but it's going to require some manipulation. This is another thing you're going to learn about macroeconomics is you try to sign these various relationships, but when you first plug through the calculus, it's not obvious what the sign of it is. And so you have to use some clever tricks to figure out the size of these effects, all right? It's not obvious necessarily how to do it. It just takes practice and experience. Here's what I'm going to do. I'm going to try to factor out of this difference some common terms. So I see here that there is a alpha minus 1 times 1 minus alpha times a k to the alpha minus 2. That's in both of them. And also this denominator, so that I'm left with a 1 as my first term. So pull out an alpha minus 1, 1 minus alpha, a k to the alpha minus 2 over 1 plus beta to the negative 1 over theta, squiggly brackets raised to the 1 minus 1 over theta. All of that is going to be times quantity 1 minus something. What is that something that is left from this garbage right-hand side term? Well, I see a theta minus 1 over theta times, let's see, what is left here? We're going to have an alpha a k to the alpha minus 1 times a beta to the negative 1 over theta times this thing in squiggly brackets raised to the negative 1 over theta. All of that is going to be divided then by the denominator of the original expression. That is 1 plus beta to the negative 1 over theta times this thing in squiggly brackets to the 1 minus 1 over theta. There we go. Does that help us in any way? Well, let's think about this. Let's suppose that theta is less than 1. If theta is less than 1, can we sign this expression? Well, what's the sign of the numerator of this first term? Alpha minus 1, 1 minus alpha, a k to the alpha minus 2. The sign of that is negative, right? Because alpha is less than 1. Remember, alpha is the term in the production function on capital. What's the sign of the denominator in that expression? 1 plus something positive times the thing in squiggly brackets is positive. It's 1 minus delta plus the marginal product of capital. Delta is a small fraction, right? So this is a positive, a negative over a positive. So the term that's multiplying this difference here is going to be a negative. If theta is less than 1, what do we know about this theta minus 1 over theta term? It's a negative, right? What do we know about this last term? Let's see, alpha a k to the alpha minus 1, that's positive. Beta to the negative 1 over theta, that's a positive number. And the thing in squiggly brackets is a positive number. Divided by the denominator of gk, that's a positive number, so the whole thing is positive, right? So this becomes a negative times a 1 minus a negative. Well, 1 minus a negative is positive, times a negative makes the whole thing negative. So if theta is less than 1, meaning that the substitution effects dominate, g is strictly decreasing. What if theta is equal to 1? Well, if theta is equal to 1, then it's, let's see, g prime is just alpha minus 1 times 1 minus alpha, a k to the alpha minus 2 over 1 plus beta inverse. The thing in squiggly brackets, if theta is equal to 1, goes to 1, because it's squiggly brackets raised to the 0 power. Now, what becomes of the term in the middle? 1 minus theta minus 1 over theta times this thing. Well, if theta is exactly equal to 1, this whole expression here goes to 0. So it's this term times 1. Well, this term here is negative for all k. So for theta equal to 1, g prime is less than 0. You might imagine, however, that if theta is bigger than 1, we're going to run into trouble like we did in the proof of the existence component. We're going to have to do some clever substitution. What if theta is bigger than 1? Well, in this case, g prime of k is going to be equal to a negative over a positive, right? Times a 1 minus, if theta is bigger than 1, this fraction, theta minus 1 over theta, is positive times a positive. So it's going to be a negative times a 1 minus a positive. Well, we don't know what the sign of that is. Is this positive number bigger than or less than 1? Hopefully, it's less than 1, right? If it's less than 1, then the whole thing is less than 0, right? If it's greater than 1, then it's a negative times a negative, and we get g prime as positive, and we're screwed. So what we've got to do is prove that this right-hand side term here is actually less than 1. Can we do that? Well, we can. First of all, theta minus 1 over theta, for theta bigger than 1, you'll see here is a positive fraction, right? Doesn't matter how big theta is. Even if theta goes to infinity, this is going to be a number that approaches 1 from below. So theta minus 1 over theta is going to be a positive fraction. Can we prove then that this term is also a positive fraction If it is, a positive fraction times a positive fraction is less than 1. Okay, well, we know that 0 has to be less than alpha a k to the alpha minus 1, beta to the negative 1 over theta, times this thing in squiggly brackets, which if you'll recall is 1 minus delta plus alpha a k to the alpha minus 1, all of that raised to the negative 1 over theta, divided by 1 plus beta to the negative 1 over theta, times this thing in squiggly brackets, but it was raised to the power of 1 minus 1 over theta. I'm going to argue that this term over here has to be less than the following. Imagine taking this first portion of the numerator, okay, and imagine adding to it a 1 minus delta. You guys see what I did there? So this first alpha a k to the alpha minus 1 in the numerator, I'm adding to that a 1 minus delta, which is a positive number. So that makes this number bigger. And if therefore it makes the numerator bigger, therefore it makes the whole ratio bigger. Well, now I can combine terms. Those two terms are actually the same, right? So that's just equal to beta to the negative 1 over theta times the same squiggly bracket term, but it's to the power of 1 plus a negative 1 over theta, divided by 1 plus beta to the negative 1 over theta times the squiggly bracket term raised to the 1 minus 1 over theta. And what do you see? Some positive term divided by 1 plus the same positive term. Well, that's just a fraction, right? X plus 1 over x has to be between 0 and 1 if x is a positive number. Therefore, g prime of k is less than 0 for all k when theta is bigger than 1. So in all cases, whether we're talking about a highly risk-averse agent or one that is more risk-neutral, in other words, it doesn't matter if the income or the substitution effects intertemporally dominate for this person, this mapping G is going to be strictly decreasing. And so K star is unique. The function G will be strictly decreasing for all K. So it's going to intersect 1 plus n at only one point. So the steps of the proof are just like the ones we did for the solo model. Verifying those steps is more difficult. Why? Because we have to consider these different cases depending on the risk tolerance of agents in the model. And in particular, the case in which theta is bigger than 1 is the trickier one. But it's still possible to show that as long as you have CRRA preferences and Cobb-Douglas production, the solo model generates the same basic type of steady state properties that the OLG model does. A unique steady state equilibrium with convergent, monotonic, stable dynamics. proposition 2 is on the stability of it, and you know, it's an involved proof as well, but goes through the same basic procedures. If you'll recall back in the solo model, the way we proved global stability was to appeal to the fundamental theorem of calculus, right? And then we showed that the capital stock had to be growing if capital was less than the steady state, and it had to be shrinking if it was greater than the steady state. We considered those different cases. You can do something very similar in the OLG model. The only problem is you have to work with implicit functions as opposed to explicit functions, because the law of motion for the capital stock cannot be explicitly solved for in the OLG model, right? You've got this weird feature where KT plus 1 is on the right-hand side and the left-hand side of this fundamental law of motion, and it can't be solved for analytically, right? And it's because the real interest rate at time t plus 1 depends on the capital stock at time t plus 1. That's an added complication to the OLG model that makes analyzing the dynamics somewhat more challenging than the solo model. I'm not going to work through that proof, but I would encourage you guys to try to take a look at it and see if you understand the steps, because it will reinforce this idea about how to solve or analyze the stability of a system, and even in a simpler model. Okay, you guys have any questions about that then? Nothing? I think this is section 4 of my notes. Again, I apologize. I've skipped around a little bit. I'm going to call this over accumulation in the OLG model. Okay. So here's what we want to start thinking about, and I'm not sure I'll be able to get through all of it today, but I will give it my best. I want you guys to start thinking about whether or not the competitive market allocation in the OLG model is equivalent to one, or how it compares to the choice of a social planner that wants to maximize the utility of all generations. Not just the 2 that are alive today, but all possible future generations. Really, the more specific question we want to ask is whether or not the competitive allocations that emerge in this OLG model are even Pareto optimal. You guys know what that concept means? Pareto optimality. It's this idea that if allocations are Pareto optimal, then you should not be able to move resources around between individuals in a way that makes even one person better off without making at least one other agent in the economy strictly worse off, right? Now, Pareto optimality can give way to some very extreme cases, right? Imagine having an economy where one guy owns everything and everybody else owns 0, right? That is technically Pareto optimal, right? Because if resources were reallocated, that one person who owns everything would be better off. Okay, that's an extreme example. But in a more realistic example, can we alter resources, move resources between generations in particular, in a way that actually improves the utility, the welfare of every generation, not just the current generation, but all future generations? Is that competitive outcome even Pareto optimal? The answer to that question in the OLG model is in general no. And that's what I want to try to demonstrate today. Now, to have that discussion, the first thing that I need to do actually is derive the aggregate resource constraint in this economy. If there was a benevolent planner, this would be the constraint that constrains the benevolent planner's actions, right? And this would be a world where there's no markets. A central, all-powerful central planner can simply drop allocations where she wants. The only thing she's going to be constrained by are the aggregate resource constraints in the economy. You can't produce more than what your production function tells you you can produce, right? So what does that look like? Well, remember, in the overall economy, output is equal to aggregate consumption plus investment. There's no government sector, there's no foreign sector. Output is given by the production function. What is investment? Investment, remember, is defined as KT plus 1 minus 1 minus delta times KT. So this is I. What is aggregate consumption? Well, that's the consumption of the young times the number of younglings plus the consumption of the old times the number of retirees. LT minus 1. All right, now we've been dealing with this model in intensive form. So we want to transform this thing into its per worker form. So how do I do that? If I divide both sides of this equation by LT, what is it going to look like? Well, what is 1 over LT times capital Y? You guys have done that exercise before. That's just output per worker, which of course is the same as the per worker production function. That follows from the fact that the production function exhibits constant returns to scale. What is KT plus 1 over LT? Well, that's KT plus 1 over LT plus 1 times LT plus 1 over LT. That's little KT plus 1 times 1 plus N. You guys have also seen that before. Minus 1 minus delta KT over LT is capital per worker. That's easy. Plus C1T times LT over LT. That's simple. Plus C2T times, what's LT minus 1 divided by LT? LT grows at rate N, right? So LT minus 1 over LT is just 1 over 1 plus N. This is the per worker aggregate resource constraint that is going to constrain the central planner's decision here. This is going to help us understand whether or not we're going to use this as our context for understanding whether or not the competitive allocations are actually even Pareto optimal in the model. Okay, I'm going to try to accomplish two things. And again, I don't know if I'm going to be able to get through both of them today. The first one, sorry. Oh, the first one is to show that the steady state of the competitive model, the one we've been working with, that does not satisfy the golden rule cannot be Pareto optimal. Let me restate that, make sure everybody understands what I'm saying. We're going to show that a steady state in the OLG model that does not satisfy the golden rule condition that we talked about in the context of the solo model cannot actually be Pareto optimal. That's one of the reasons why we introduced the golden rule in the solo model, because I told you we would come back to it in the context of these other models. It would be helpful helpful for us to think about some of the properties of these other models. The second thing we're going to do is show that the basic OLG model does not rule out these what are called dynamically inefficient economies. Or dynamically inefficient equilibria, I should say. So there's two parts to this. We're going to show that the competitive equilibrium steady state of the OLG model that does not satisfy the golden rule, and in general it will not, cannot possibly be Pareto optimal, meaning or implying that we can rearrange resources in a way that makes everybody's life better off, including all future but yet unborn generations. And then to solidify this, we're going to show that the basic OLG model, in fact, we'll use the canonical model as an example, does not rule out these dynamically inefficient equilibria, that it's not just a theoretical curiosity, but in fact, it's a real possibility. Okay? So am I getting feedback from something? Sorry. So the OLG model is the first example in our class of a model that does not satisfy necessarily Adam Smith's invisible hand principle. It does not satisfy the first fundamental theorem of welfare economics, where the competitive outcomes are necessarily supported as a Pareto optimal outcome. Okay, how am I going to do that? Let me define a little bit of notation here. I'm going to define little ct as the sum of C1t and C2t over 1 plus n. In other words, it's the per worker level of aggregate consumption in the economy. K star and C star are going to be the steady states of our competitive economy. So they're the steady states that we've analyzed already. That's what I'm going to denote those K star and C star. Okay, so we can already go back to this aggregate resource constraint and characterize how K star and C star are related, right? F of K star must be equal to K star times 1 plus n minus 1 minus delta times K star plus C star. Some of this cancels, right? And so you can write steady state consumption as F of K star, let's see, minus delta plus n times K star. Let's consider the effects then of an increase in steady state consumption on, increase in steady state capital on steady state consumption. What's the partial of C star with respect to K star? It's F prime of K star minus delta plus n. You guys recognize that? This is going to be greater than or equal to 0, depending on whether or not F prime of K star is bigger than or less than delta plus n. That is, whether the marginal product of capital is greater than or less than delta plus the population growth rate. Now, do you guys recall what the golden rule level of capital satisfies? the golden rule level of capital says that the marginal product of capital evaluated at the golden rule level of capital is equal to delta plus n. The slope of the production function had to be exactly equal to the slope of that break-even investment schedule. So this implies then that per worker consumption in a steady state is actually decreasing in steady state capital if the steady state value of capital exceeds the golden rule, right? And that's because the production function is strictly concave, right? Think about this. If K star is bigger than the golden rule, then that means F prime is getting smaller, right? And if it's equal to delta plus n at the golden rule, that means that any K bigger than the golden rule, you're going to have F prime less than delta plus n. And if F prime is less than delta plus n, dCdK is negative. So steady state consumption is actually decreasing in the capital stock for any value of capital that exceeds the golden rule. This is what's known as a dynamically inefficient equilibrium. It's any equilibrium where K star is bigger than the golden rule. The second part of this discussion, which it looks like I won't get to until the next class, is supposed to argue that or suggest that these dynamically inefficient equilibria where we've overaccumulated capital above the golden rule are very possible in the OLG model because of these pecuniary externalities that I keep mentioning. All right, the fact that future generations' preferences are not reflected in current transactions.
Would it be dynamically inefficient if you underaccumulated capital too?
Yes. The only problem with that outcome is that if you're saving too little, there are no policies whereby you can increase the capital stock, but don't end up harming some individuals. And the reason is that, think about it, if you're saving too little and the government mandates that you were to save more so that capital will go higher, so that consumption will be higher in the future after you're long gone, future generations will benefit from that, but you're going to experience a cost because if you save more today, that's less you consume, that lowers your utility. So it is dynamically inefficient, but it's not as straightforward. The same Pareto optimality arguments can't be applied to it. That's what I'll say about that. I think you'll see a little bit more when we get into this discussion in greater detail with these fiscal policies in the next class. There's another way of writing these dynamically inefficient outcomes. That is sometimes useful. It's by recognizing that in a dynamically efficient world, right, dCdK, which is equal to F prime of K star minus delta plus N. So in a dynamically inefficient world, that this derivative is negative. That is in the case in which then we've overaccumulated capital. Well, the marginal product of capital minus depreciation is equal to what? What's F prime minus delta equal to? The real return to capital. So a dynamically inefficient economy is one in which the real return to capital is actually less than the population growth rate. That's another way of expressing the same situation. You will find that this relationship is sometimes easier to work with. all right? But it's equivalent to the one I just did on the past page. You can either say that the marginal product of capital is less than delta plus n, or alternatively, that the real return to capital is less than the population growth rate. Okay, what I want to do now, I think this is proposition 3 in the notes. I want to prove that the steady state in which capital exceeds the golden rule. So this steady state where we've got K star bigger than the golden rule is not Pareto optimal, which means that we should be able to rearrange allocations in a way that makes everyone better off. Hopefully, going through a sketch of this proof will help you understand the fiscal, tax, and transfer policies that we're going to consider in the next class, because it's getting at the same basic idea. Okay, here's how I'm going to sketch this proof, all right? Let's suppose that at date t, cap t that is, the economy is in a steady state, a competitive steady state, where K star is bigger than K star gold. So our economy has settled down into a competitive steady state that is dynamically inefficient. That is where R star is less than N at date cap T. So that's far out into the future, okay? I want you guys to think about the following variation. So imagine that a benevolent central planner could simply take resources and move them around to different uses. Here's the variation I want you to consider. Imagine a planner that is able to reduce the capital stock for the next period, that is K cap T plus 1, by some small amount. Let's call it DK. And then hold the capital stock at that level forever. All right. Now that's clearly a feasible plan, right? In this world where we have homogeneous goods, you can either eat the corn for consumption or grow it for new consumption later on, right? And so we can, reducing the capital stock and consuming it is a feasible option. All right, so KT plus 1 then is going to be reduced by some amount, let's call it DK, where let's say DK is a small amount that's somewhere, it's greater than 0, but it's less than the distance between steady state capital and the golden rule level of capital. In other words, the central planner is not jumping us all the way to the golden rule level of capital in one move, okay? But this is some small incremental reduction in the capital stock, we'll call it DK, that occurs at KT plus 1, as well as all future dates. Everybody see what I'm talking about there? So here's the variation. The central planner lowers the capital stock at date cap T plus 1, and then keeps the capital stock at that same level for the rest of eternity. The question is, how does this affect consumption allocations moving forward? Utility only depends on consumption. Does this make our consumption strictly better off always? Well, what is consumption at date cap T equal to? If we go back to the aggregate resource constraint, we know that it's equal to total production at date cap T plus, let's see, 1 minus delta K cap T minus 1 plus N K cap T plus 1. I think I have that right. Yes. CT should be equal to F plus 1 minus delta KT minus 1 plus N KT plus 1. Again, this just comes from the resource constraint. That's why I derived that thing first. Okay, what happens to consumption at date cap t if the planner carries out this variation? That is, how much is consumption going to change instantly at date cap t? That's what this notation means, by the way. So don't get confused by this. This delta C cap t here is not CT minus CT minus 1. It's not the first difference. It's how much your consumption is going to change in this period if the central planner was to implement this variation, this reallocation. Well, it would be equal to what? F prime of K cap t times whatever the change in K cap t was, plus 1 minus delta times the change in K cap t, minus 1 plus n times the change in K cap t plus 1. Well, what is the change in K cap t? It's 0, right? What the planner is doing here is she's observing K cap t, and then she is reducing capital stock for period t plus 1 and all future periods. So the change in K cap t, that's the state variable for period cap t, stays the same. What changes is K cap t plus 1, right? And how much is K cap t plus 1 going to change by? It goes from K star to K star minus dk, right? Or I'm sorry, by the negative of that amount. Capital drops by an amount delta K. And so this becomes 1 plus n times, not delta K, I'm sorry, dk. I don't mean to confuse you on the notation there. Right? How much does the capital stock change by for period cap t plus 1? It's going to fall by an amount dk. So how much is consumption going to change then? It's negative 1 plus n times a negative dk. That's just 1 plus n times dk, which is positive. So, and look, that's kind of obvious, right? If we lower the capital stock today, you take those resources that are capital and you allow the current generations, that's C, that's both the young and the old, to consume more, right? The planner can simply divide that consumption evenly between the young generation and the current old generation, right? So we draw down the capital stock today, and everybody is going to be better off today because they're going to be able to eat more corn. The question is whether or not all future generations are going to be better off, right? The central planner cares not just about us today, but our children who are yet unborn. Well, what happens to consumption at date t plus 1 here? Well, again, let's just go through the math. It's f prime K cap t plus 1 times the change in K cap t plus 1 plus 1 minus delta times the change in K cap t plus 1 minus 1 plus n times the change in K cap t plus 2. All right, we just scrolled that equation forward one period. Well, what's the change in K cap t plus 1? It's negative dk, right? So this is negative f prime of, what's K cap t plus 1 equal to? Well, it's just K star minus dk times negative dk minus 1 minus delta times dk. That's the change in K cap t plus 1. Let's see, minus 1 plus n. What's the change in K cap t plus 2? Well, remember, this is a permanent drop in capital. So capital 2 periods from now is also going to fall by dk. So this becomes a plus 1 plus n times dk. some of this cancels. And you will be left with a negative f prime of k cap t plus 1. That's just the steady state value of capital minus this variation that the central planner is considering, minus a delta plus n, that whole quantity, times dk. You can factor a dk out of this term. Now, fortunately, we can sign this. Why? The marginal product of capital, as long as the capital stock is above the golden rule, is going to be less than delta plus n. This is a dynamically inefficient economy. So f prime minus delta plus n is a negative number. A negative times a negative times a positive is a positive. So the change in consumption at date cap t plus 1 is positive as well. Now, we can play this game a number of times, but what you're going to find is that the change in c cap t plus I is also positive for all I greater than or equal to 1, meaning that this variation in the capital stock that the central planner is considering will improve not only the current generation of people today, but it will also improve the utility, the welfare of all future generations. And the planner can simply divide these extra resources up evenly between whoever's old in that period and whoever's young, and everyone will be strictly better off. So what we've demonstrated here is that the competitive equilibrium of a dynamically inefficient economy, one that has saved too much and overaccumulated capital, is not Pareto optimal. That we can rearrange resources in a way that makes all current and future generations strictly better off. That's actually pretty obvious or intuitive, right? Now, we don't live in a world where there is a benevolent central planner. We do live in a world, however, where policymakers can design tax and transfer schemes that do something very similar to this. By taxing us in a certain way, it might actually discourage savings in a way that's very similar to this variation that we've considered. So is there a tax and transfer scheme that can be implemented that would help move this dynamically inefficient economy closer to the golden rule? The answer to that question is yes. And in the next class, we will go through some examples of that and hopefully work through a proof of what I'm talking about there. There's two kinds of tax and transfer schemes. There's the fully funded Social Security program versus what's called a pay-as-you-go Social Security program. We're going to analyze both of those in the context of this model. Now, the last thing I need to do before I get there, and I'll do this at the beginning of next class, is the second part of this argument I wanted to make. What have we done so far? We've shown that a dynamically inefficient economy is not Pareto optimal. A central planner can rearrange allocations in a way that makes everyone better off. What I want to show you in the next class is that that's every bit, that's a distinct possibility in the OLG model. In fact, in most cases, the competitive outcome is not going to be equal to the golden rule. That given certain parameter values, we could very easily converge to a steady state in the competitive equilibrium where R is less than N. So we'll just do a quick numerical example of that in the context of the canonical OLG model with logged preferences. And then we'll immediately start discussing these pay-as-you-go and fully funded Social Security tax and transfer schemes. We probably won't be able to finish everything by the end of class on Wednesday. So this will likely bleed in a little bit to next Monday. After that, we'll be ready to start our next discussion on dynamic programming. Okay, so we're actually not going to talk about economics for a few days. and just review the basic mathematical tools that are needed to solve and analyze infinite horizon optimization problems. The OLG model is a 2-period optimization problem. Well, what happens if we live in an economy where agents live forever, right? And they want to maximize a infinite discounted sum of future utilities. It turns out we need a different set of mathematical tools to characterize the solution to those types of problems so that we can analyze whether or not those models have a steady state and what the stability properties of those growth models are. Okay, so we're gonna take a bit of a break from the actual econ and review the basic mathematical concepts that are, or tools that are needed to work with that class of problems. That's probably going to take 2 to 2.5 days to get through. Then we'll be able to move into what's called the deterministic optimal growth model, the basic neoclassical growth model, representative agent. That'll be the third kind of workhorse framework that we're going to talk about this semester. That's all I have. So let me end this.